Welcome to the third lecture of Introduction to Kinetics. My name is Rodrigo Albuquerque, and these slides can be watched here. Can be found. The links to these slides can be found at my homepage, labsupercam.com, under Teaching. These videos can be also found in YouTube. So today I will review the last lecture and define half-life of reactions and introduce the method of initial rates. In the last lecture, we have defined the integrated rate law, which is just an expression that gives the concentration of a reagent as a function of time. For a zeroth order reaction, the concentration of the reagent is given by this expression. So this is the integrated rate law for the zeroth order reaction, where you can calculate the concentration of A as a function of time, provided you know the initial concentration of A and the rate constant K. If you have a first order reaction, the relation between concentration and time is shown here, or alternatively by this other expression. And if you have a second order reaction, you would have this relation between concentration and time. In all cases, it's possible to take the data of concentrations against time, build a table, and we can plot these points, concentration against time, and we can now make a linear regression like this, so that we can find the gradient or the slope, which is A, which would be minus K in this case, minus K in this case, or K, and the intercept B, which would be in this case initial concentration of A, or logarithm of the initial concentration of A, or 1 over the initial concentration of A. In all cases, it's possible to, if you plot the concentration of A against time, if you get a line, you get zeroth order reaction. If you plot the ln of A against time and you get a line, a straight line, your reaction is first order in A. And if you plot 1 divided by concentration of A against time, and if you get a straight line, your reaction is second order in A. Okay, so this we'll discuss in last lecture. So today we are going to talk about the method of the half-life. So how to calculate the half-life. Let's imagine a simple reaction A given B. And we remember the integrated rate law for a zeroth order reaction is given by this expression here, where at time 0 we have the initial concentration of A, which is A0, and at time t we have a specific concentration of A. Now, we could ask, how long does it take for this initial concentration of A to decrease to half of its value? Which means if you have here 0.5 molar, how long does it take for the concentration of A to go from 0.5 molar to 0.25 molar? So this time is called the half-life of A, and is expressed as a T half. And it can be shown here. This we are plotting for a zeroth order reaction, the relationship between the concentration of A and time. And you see that the reagent, the concentration always decreases, but it decreases linearly, as shown in this red line. And the time necessary for the concentration to go from A0, from any initial concentration, to half of its value, which is A0 divided by 2. So this time is shown in blue here, so it's T half. And if you take this point as a new initial point, so the time necessary for the concentration to go from this value here, A0 divided by 2, to A0 divided by 4, is T half, shown in green. So we can see that the half-life, in this case, always decreases. And how can we predict an expression for this half-life? So let's just take the initial concentration and substitute the final concentration of A by half of the initial concentration. So at time t, at time 0 we have the initial concentration, A0, it's shown here. And at time t half, so I need to put here t half, the concentration of A would be half of this initial concentration. So you just need to substitute here concentration of A as half of the initial concentration. So we just add this here. Instead of t, we show t half. Now we just need to isolate t half. And t half is shown here as the initial concentration of A divided by 2K, where K is the rate constant of this reaction. Now we can see here that T half is proportional to the initial concentration of A. So if you have here initial concentration of A equal to 1 molar, you would have 1 T half. If you have now a different initial concentration of A, let's say 0.5 molar, now the new T half would be half of the previous one. So T half keeps decreasing just because the initial concentration at every new point keeps decreasing. The concentration of the reagent always decreases upon time. So T half becomes gradually smaller, as we can see graphically here, and we can also see from this equation. So in this case, the new T half is equal to the previous one divided by 2. If you just take successive points, if you sequentially take points and the new points correspond to the previous one divided by 2. The new concentration is the previous one divided by 2. So you keep decreasing the concentration by a factor of 2. If we have now a first order reaction, just remember there's the integrated rate law, and at time t we have the concentration of A. At time 0 we have the initial concentration of A. Now let's do the same as we did before. So for a specific time t half, the concentration of A would be the initial concentration divided by 2. So we just substitute in this expression where I have concentration of A, I put concentration of A divided by 2, and where I have T half, where I have T, I substitute by T half. And now I just isolate T half to predict its value. In this case, I take ln of concentration of A, initial concentration of A, put to the left side to get this here. The difference of logarithms is the ratio between these two logarithms. So I can combine these two in this way. And in this case, initial concentration of A just disappears here. And I get ln of 1 divided by 2. So ln of 1 divided by 2, I can put 2 to the power of minus 1. So the minus 1 could go out of the logarithm and to multiply logarithm. So now I have minus 1 multiplied by ln of 2 equal to minus k t half. And I multiply by minus 1 this expression to finally get an expression for t half for a first order reaction. So first we can see that t half is constant, doesn't depend on any concentration in this case. And in fact, if we look at the dependence of the concentration with time for a first order reaction, we can see that the time necessary for the concentration to go from 1 molar to 0.5 molar, which means to half of its initial value, is T half, this T half shown in this red region. Now if I take 0.5 molar, and the time necessary to go for the concentration to go from this initial value of 0.5 molar to 0.25 is precisely the same T half as before, shown in this orange region. And then we keep doing this, and we can see that all half-lives are the same. So they don't change. So graphically we can see this here, and analytically we can see this expression that doesn't depend on concentration. If you have the rate constant k, you can promptly calculate t half, which is going to be always constant. So this is typical for a first order reaction. And just remember, when we are analyzing the half-life of any reagent, we shouldn't plot the integrated rate law. So in this y-axis, we shouldn't put ln of A, but we should put just the concentration of A against time. So every time we analyze the method of half-life, we just put the concentration here and time. And then we can visualize what happens with the concentration upon time. The last case is for the second order reaction. So this is the integrated rate law for second order reaction, as we have seen in the previous lectures. And we just substitute time by T half, where the concentration is going to be half of the initial concentration. We just put here 1 divided by initial concentration of A divided by 2 and T half. Now again we isolate T half, but first let's add 1 divided by the initial concentration of A to the left side, just to solve this expression, and we get this here. And now we can just isolate T half. So T half is going to be 1 divided by K multiplied by concentration of A, initial concentration of A. So in this case, for second order reaction, T half depends again on the initial concentration. And since the initial concentration of the reagent keeps decreasing along the reaction, and this number here in the denominator of this fraction keeps decreasing, T half keeps increasing. So T half is inversely proportional to the concentration of A, to the initial concentration of A. So T half always increases. And we can see graphically here, we have again the concentration of A against time, and we can see that to go from 0.2 molar to 0.1, which is half of this value, we need some time. So this is the first half-life. This time is perhaps 50 or 40 seconds in this scale. Now, to go from 0.1 molar to half of its value, which means to 0.05, we need now longer time. So the second half-life is larger. And if we do this again to 0.05 to 0.025, we need even longer time. So we can see graphically that the half-life of a reaction, of second order reaction, keeps increasing, as also seen by this expression. Again, when we are analyzing half-life of a reaction, we shouldn't plot 1 divided by concentration of A against time, but rather we should plot the concentration of A against time. So every time we show concentration against time, because we are just interested in looking at the dependence of the concentration with the time. Now let's do a task. A student investigated the reaction A given B and found that it took 2 seconds for the concentration of A to decrease from 0.4 molar to 0.2 molar, and the same time to decrease from 0.2 molar to 0.1 molar. Now predict the rate law and rate constant for this reaction. You can just stop this video and play again to see the solution. The solution is given here. So if T half is constant, we have learned that this means we have a first order reaction. And in this case, if T half is constant, for the first order reaction, T half is given by ln of 2 divided by K. or K is equal to ln of 2 divided by T half. So T half is 2 seconds. We just substitute in this expression here, and we get K of 0.35 second minus 1. The rate law, since it's a first order reaction, we have this rate law. Vt is equal to K concentration of A. In this case, the correct answer would be the first one, A. Vt is equal to Ka, and K is equal to 0.35 second minus 1. Now let's introduce the method of initial rates. This is used to predict rate laws from kinetic experiments. So let's imagine a very simple reaction, A given B, and the initial rate of this reaction I'm expressing as V0 at time 0, which is instantaneous consumption rate of the reagent A at time t0. In practice, it's never possible to get precisely the time t0, so we wait a little bit. In the beginning of this curve, here we see the concentration of A as a function of time, so we just wait a little bit to calculate the gradient of this line. So we have 2 points. The first one is t time equals to 0. And the second one, let's say, is after 1 second or any short time period. And the gradient of the slope is the derivative concentration of A divided by time, so it's infinitesimal variation of concentration divided by infinitesimal variation of time. And now in practice, this dash green line is shown here. So in practice we have 2 points. The initial point shown here at time 0, and we wait a little bit of time, so at time t1 could be, I don't know, 1 second, let's say, and we have a second point here. So now to get the gradient of this dash line at this initial part of this curve, we just do V0 is equal to the final concentration at this point, which is A1, minus the initial concentration, which is A0, divided by final time, which is T1, minus initial time, which is 0. So if you wish, it's delta y divided by delta x. And we have a minus sign because of the rate of reaction is always positive. And in this way, if we wait a little bit of time and see and measure the new concentration of A, we just substitute here to get the initial rate of this reaction. So what do we need to do? We run the reaction and measure concentration of A at time t1. So we should know, of course, the initial concentration of A that you have in the experiment, and we just measure the concentration of A at time t1, and we use this formula to calculate V0. And then we run again the reaction using different initial concentrations of A. Now, we have, in this case, 2 experiments. In the first experiment, the initial concentration of A was 0.1 molar. And if we use our data here, so I'm not showing the time, but the V0 was 1 molar per second. A second experiment was done using initial concentration of A as 0.2. In this case, I calculate again V0 and I found 4 molar per second. Now, I just propose this general expression for the rate law, which is the initial reaction rate is equal to K multiplied by the initial concentration of A to the power of X, where X is the order of reaction with respect to reagent A. Now I just substitute these values inside this equation. As you see here, 1 is equal to K. I put here V0, it's shown here 0.1, and V0 is 1 here, and concentration of A is 0.1. In the second reaction, I have 2 different values. for V0 concentration of A, I have two equations. Now I just need to divide. Let's divide the first by the second equation here. In this case, I get 1/4 is equal to this amount, where we can see that x is equal to 2. So alternatively, you can also apply the logarithm on both sides of this relation. Logarithm of 1/4 is equal to logarithm of this here. And if you have logarithm of a to the power of b, this is equal to b multiplied by the logarithm of a. So if you have any exponents here, this exponent can go out of the logarithm and multiply the whole logarithm. So this is another way of solving this very easily. So this x just would go in front of the logarithm of 1/2, and then x is equal to logarithm of 1/4 divided by logarithm of 1/2, which means x is equal to 2. Now we can just use x equal to 2 in any equation, the first or the second of these here equations, and we get k is equal to this. And if you use the correct unit here in the concentration, the correct exponent, the concentration of the units of k come automatically. So here we have concentration of molar -1, second -1. Just remember the units of reaction rates are molar per second. And now the rate law, this is a second order reaction because x is equal to 2. So we would have 2 here. So we can generalize this expression for any time, and Vt is equal to k multiplied by concentration of A to the power of 2. So this would be the rate law according to the method of initial rates applied to this specific reaction. Now let's do the graphical method. We have again this general expression. We don't know who is this exponent, which is the order of the reaction with respect to A. And now let's apply the logarithm on both sides. So this will be logarithm of V equal to logarithm of K plus logarithm of A0 to the power of n. Just remember, the logarithm of any product would be the sum of the logarithms of the separate parts. So logarithm of AB is logarithm of A plus logarithm of B. So we just apply this. We have here now logarithm of K, this side, and just remember that n can multiply the logarithm of the initial concentration of A. So this n was here previously, and now it can go here. I'm just using this property of logarithm, and now we get this expression here. Now this is similar to the equation of a straight line, where I can see that I can identify this amount here, log of V0 as the y, and log of initial concentration of A as the x. In this case, the slope would be my exponent n, and the intercept of this equation would be logarithm of k. So now we have the intercept here and the gradient, and we just need to take data from experiments. So let's take the data from the previous experiment. So if you take the previous two experiments, the initial concentration of A, I just apply logarithm, I would get -1 and -0.7. And if I apply logarithm of the initial rates, I would just get 0 and 0.6. Now, what we need to do is just to make a plot of this equation here. So we plot in the y-axis logarithm of the initial rate, and the x-axis I plot logarithm of initial concentration of A. I have 2 points. Ideally, I should have 3 or 4 many points so that I can get a nice regression. I have a nice line, straight line. But let's take this very simple example. If I get a line, I can make a linear regression using, for instance, Excel. In this case, the gradient was 2. and the intercept was also 2. So the linear fit of these 2 points was given by this equation. Now we can clearly see that the slope or the gradient is 2, which means our exponent n is 2. And the intercept, which is log of k, is equal to 2. So we have n equal to 2 means second order reaction, and log of k is equal to 2, which means k is 10 to the power of 2 molar minus 1, second minus 1. The units are typical for second order reaction. So finding the rate law would be given by this expression here. So this reaction is second order with respect to reagent A. Now let's complicate a little bit. Let's use 2 reagents, A and B. In this case, our rate law is going to be a bit more complicated, where X and Y are the orders of reaction with respect to reagents A and B, respectively. Now we run several reactions varying either concentration of A or concentration of B each time. So the first experiment, I have any parameters of concentration of A, concentration of B, and I measure the initial rate as previously described. Now the second experiment, I kept the concentration of B constant, so it's the same, but I increased concentration of A. And now in the third experiment, I kept the initial concentration of A constant in relation to the first experiment, so it's the same, and I increased the initial concentration of B, and I measured again the initial rate. Now I have my general expression for the rate law. I don't know who is X, who is Y, but let's calculate X and Y. So now I just need to take this data here, concentration of A, B, and the rate, initial rate, just put here in this equation. So in the first equation I have this, second equation I would have this, and the third one I have this here. Now I just need to combine equations where only one concentration changes, while the other remains constant. Which means let's divide equation 1 by 2. So the first divided by the second. So if you divide this by this, is 1/2. This by this, so k just disappears, and we get this divided by this, which is just 1/2 to the power of x. So x is equal to 1. Which means the reaction is first order with respect to reagent A. Now I do the same, but now having equations 1 and 3, because from equations 1 and 3, concentration of A, the initial concentration of A is constant, just concentration of B changes. And then if I divide the first by the third, I get this expression. So y in this case equal to 2. We don't even need to apply this logarithm to calculate this. So this is straightforward. And using x and y in any equation, we now obtain the rate constant k. So k in this case is 2000 molar minus 2, second minus 1. So the rate law in this case is given by this expression, where the reaction is first order with respect to A and second order with respect to B. Let's now complicate a bit more, so let's use the isolation method. So the isolation method means let's use an excess of any of the reagents, so either of B or of A. In this case, let's use the excess of reagent B. If B is in excess, this means the concentration of B that we have in the beginning doesn't change. So the initial concentration of B is a constant. So we have here the initial concentration of B is a constant. So that our rate law can be simplified, can be expressed like this, where we have the effective rate constant K, and we have the initial concentration of A to the power of M. So in this case, the initial rate only depends on the initial concentration of A. And who is the effective K? Effective K is given by this expression. It's just the real K, the real rate constant, multiplied by this constant value of concentration of B to the power of N. And where M and N are the reaction orders with respect to A and B respectively. Now, let's just take this first expression on the left side. Let's apply the logarithm on both sides. So logarithm of V0 is equal to logarithm of the whole thing here. So logarithm of the product is the sum of logarithms, as we show here. And the exponent can go out of logarithm. It would be multiplying logarithm of initial concentration of A, as we show here. Now we have an expression that's similar to the linear equation. And we just need to plot, now in the y-axis we plot logarithm of V0, as shown here. And the x-axis we plot logarithm of the initial concentration of A. We have here two experiments. In both cases, the initial concentration of B is the same, so it's always constant. If we have these two points, we can now make a linear regression to get the gradient or the slope, which is just this exponent here, and to get the intercept. The intercept is log of the effective K. So that we have now, for this initial concentration of B, which is constant, we got the effective K. Now we make the same plot again for a different initial concentration of B. So we just change, but still in large excess. So we change the initial concentration of B. We use another value of it. It's still in large excess, so it's still constant. And we get 2 points where we are just changing the initial concentration of A for different points. And we make this plot again. We are going to get the same gradient M, but a different effective K, so that we find a new effective K. Now we have, for the previous B0 we used, we have the effective K, and for a new B0, I'm calling B0 prime, we find effective K prime. Now I have two new points, and I specify these points as B0 and effective K, and B0 prime, effective K prime. I just need to plot these 2 points here using the second part, using the expression of the effective K, because I have just concentration of B0 and effective K in this equation here. So let's just apply the logarithm on the left side and on the right side of it, and we get this expression here. And the logarithm of K multiplied by anything is the sum of logarithm of K plus and there's the other part. So the n is an exponent, can go out of the logarithm, as we already see. And now we have the linear equation here. So this is y is equal to ax plus b. We just need now to plot this here. So now in our y-axis we have logarithm of effective k. In the x-axis we have logarithm of the initial concentration of B. We are just plotting this equation. If we have these 2 points, which are shown here, so these 2 points, we can now make a linear regression, and then from where we find the gradient or the slope, which is n, and we can also find the intercept, which is logarithm of k from this equation. So finally, the second plot here using effective k against concentration of B gives us the exponent n and the real rate constant for this reaction, so that we can get now m from the first plots, from the first two plots, you get m, and from the second plot, you get n and k. Now we know m, n, and k, and we know the rate law for this reaction, and we also know the value of k in this case. So that there's a way, graphical way to determine rate laws using initial rates in the isolation method. So in this case, we use a large excess of B, but we could have used a large excess of A, and we would do the contrary, what we have done. Now let's do an exercise. So this reaction was investigated by the method of initial rates, given values of the initial concentration in molar and initial reaction rates in molar per second. So we have 3 experiments shown here, and you need to predict now the overall reaction order and K. Just stop this video and try to solve this problem and play again when you want to see the answer. And this is a solution for this problem. First of all, for this reaction, there are 2 reagents here. We just write a general equation, a general rate law, which is k multiplied by concentration of A to the power of x, concentration of B to the power of y. And for this general expression, we don't know who is x and y, but we now substitute the initial rates and concentrations on this expression for each single experiment shown here. So we have now these 3 equations. And we now divide the first by the second equation, just because if you compare the first and the second equation, one of the concentrations is constant, which is concentration of A. The initial concentration of A is constant, while the concentration of B changes. That's why you are comparing 1 and 2. You are dividing 1 by 2. And then we get this here, and y in this case is equal to 0. If we now combine equations 1 and 3, just because in this case, in going from 1 to 3, the concentration of B is the same, but the initial concentration of A changes. And now we divide equation 1 by equation 3 to get this here, and x is equal to 1. Which means now I know x, I know y, I just substitute in any of these 3 equations to get the value of k. So k is, in this case, if you use the correct units for initial rate, initial reaction rate, and concentration, you just get the correct units for K. So in this case, the overall reaction order is X plus Y. So X plus Y is 1. So we have here. This would be the correct answer, would be letter B. Okay, the key topics in this lecture I show here. For zeroth order reaction, we have this integrated rate law, as you saw in the previous lecture, but then we can calculate the half-life using this expression here. So half-life becomes gradually smaller upon proceeding the reaction. This happens because the reagent A, the concentration of this reagent always decreases during the reaction. So if this decreases, T half also decreases because this is directly proportional to the concentration of A. Now, for the first order reaction, we have this integrated rate law, and the half-life is given by this expression where you don't see any concentration dependence here. So T half is always the same, doesn't depend on the concentration. If we have a second order reaction, we have this integrated rate law, and we have this half-life. Now T half keeps increasing because it's inversely proportional to the initial concentration of A. Since the concentration of this reagent keeps decreasing along the reaction, this denominator keeps decreasing and T half keeps increasing. So T half is inversely proportional to this concentration. Finally, the method of initial rates, we find the reaction orders and K. So it's an interesting method to use where you determine the concentration at the very beginning of the equation of the reaction and you can calculate reaction orders in K and of course rate laws. The graphical method can also be used for the method of initial rates as I show here. And finally, the isolation method can be combined with the method of initial rates to predict also rate laws.